Well, thank you very much. This work is joint with Donald Martin, who's at NC State, and Michael Peng, who was my PhD student until last week. And basically what we're going to be looking at today is how, in many applications, what we're really interested in is patterns in the data rather than sort of single time points. So what we want to know is whether we can do some kind of algorithm that allows us to sort of have the flavor of sort of the exact nature of things that we get from sort of map estimates and dynamic programming, but also take into account the uncertainty that we would get if we kept sampling the data. So the outline is basically, I'll give you an introduction into the kind of problems we're interested in and give you a real data example of why this might be interesting. I'll then explain the kind of method we're going to use, which is based on something called finite Markov chain embedding, and basically show how there's a relationship between runs in the data and something that you could define as change points. And this will be a sort of an example of the type of patterns we're interested in. And then we'll go back again to the real data analysis and see what difference it makes, and a few conclusions. So what actually am I going to be talking about today? Well, basically I'm going to be talking about patterns, which I'm going to define sort of quite generally as sort of just being a function of one or more time points. Of most of the patterns that are of interest are actually going to be sort of more than one time point. For example, just looking quickly, here you've got the pattern 1, 2, 1, and you've got some kind of data sequence, and we see straight away that the pattern is in the data sequence. Now, there are many types of patterns that can be of interest. There, for example, can be runs in sequences, which sort of, looking to see how long something happens until it changes to something else, which is sort of a run. You have in genetic sequences, you have sort of promoter regions, and these basically can be defined as certain particular classes of states, and therefore these make up patterns because it's more than one particular location. It's a block of locations. Economic data, often people define recessions to be a downturn in the economy over a certain period of time, so therefore you have to take into account more than one individual time point. So all of these things can be seen as patterns. So we're going to be sort of looking at this kind of general setup. Basically, lots of patterns of interest are in the hidden sequences. If they're in the observed sequence, then you just go look for them. If you can see the observed sequence, you say, okay, it's there. But in many of the applications we're interested in, the patterns that we're actually wanting to find are patterns that are functions of the hidden sequence. So therefore, we need to somehow be able to sort of interrogate the hidden sequence and see if we can get some sort of probabilistic results about the patterns within those hidden sequences. I'm going to be talking today about using hidden Markov models, which we've had a lot about in the conference already. But this sort of framework that we're going to suggest actually works in sort of pretty much most Bayesian network kind of graphical models. So it doesn't have to be a hidden Markov model, but for ease today, it's going to be easy just to talk about hidden Markov models. I'm going to talk about fairly general hidden Markov models, although you can use whatever sort of flavor of hidden Markov model you like. The model here is going to be dependent on some past observations and also our number of previous states. If you want to just make it a sort of standard hidden Markov model, you can forget about the previous data, and you can just set r equal to 1. So you just have it dependent on one previous state. But basically, we're going to have the sort of observation equation sort of standard, and then the standard Markov assumption on the hidden sequence. We can make this more general too. It's just going to change the sort of overall order of the system, but it can be easily handled. So it's just sort of general standard hidden Markov model that we'll be examining today. As we know that there are lots and lots of applications of hidden Markov models we've seen many already, but sort of speech recognition, image processing. DNA sequence analysis is what I'm going to be looking at specifically today, but there are many other applications of which patterns are the thing of interest. It's not just the particular classification at each point. You need to worry about the whole pattern, and I'll show you why. So what's the sort of current ways people do signal segmentation, for example, which is a kind of pattern detection? As particularly in the biological application, what happens is that people define the map estimate. They get the Viterbi algorithm and they just find the maximal probabilistic sequence and then treat it as fixed. Say, well, this is the sequence that's really underlying, and then let's go and search for our patterns because that's the easiest way to do it. But in real terms, we know that this is just one particular sequence that happens to have the highest probability. If we look at other sequences, they may be very different, and therefore the patterns will be very different. So this certainly, if you take the Viterbi sequence, it does not guarantee to give you the most probable set of patterns. It gives you the most probable sequence overall, but not the most probable set of patterns. You could do something else. You could do smoothing, so just literally look at the individual states and then say, well, maybe I'll just search that and look for patterns within that system. But again, you have the same problem. The obvious solution is, we're going to do some form of MCMC often in these kind of models. Let's just keep all our MCMC states sequences that we generate, and then let's sort of build a distribution on that. But the problem with that is that, of course, we have sampling error. And so for patterns, it becomes a little more difficult to classify how much sampling error we have in relation to our patterns rather than in relation to the whole sequence. So what we'd kind of like to do is see if we can do something in the middle. So what we'd like to do is somehow get some form of distributional estimate, as if we would from sampling, but somehow make it exact. So not have to worry about the sampling error. Now, the nice thing is, because of the structure of the models, we can actually do this. And so what we're going to do is propose this new methodology, and for a particular case of runs, although it works for much more general patterns too, we're going to show that we can, by defining a duality between runs and change points, we can look at sequence segmentation simply in an exact method by basically building bigger Markov models that we can then look at. So, very simple underlying idea, and I'll then come to a more real application. Say we have some data and a hidden layer, and basically we want to segment it. Well, we see that we could classify this into 4 different segments. The first segment ends here when the A's stop, then there's one time point with a B, some C's, and then we go back to A again. So there's 4 segments in this data. But it may not be of interest if the segments don't last very long. In lots of applications, we really need to see something continuing for a certain amount of time before we are happy to say, well, it really is doing this. So maybe we want to say, okay, well, we're only interested in segments that last at least 2 time points. So we still have this first segment here, then we don't count this because it's not of interest. We see another segment here, and then we forget this one, so this only has 2 segments in. So depending on what you are prepared to say about your application, about what the sort of interesting patterns are, then it may be that the number of segments is very different. So the obvious way to do this is to say, well, okay, I could just really enumerate my whole set of possibilities and condition on my data, look at the probabilities. And what I would really like to do is sum all these different things for the particular patterns I'm interested in. If I'm interested in patterns that have to last at least 2 points, for example, well, I'd sum this one, and I'd sum this one, and then I'd sum this one for this part and say there's actually a second one here. So this only has 1 pattern in it, this only has 1 pattern in it, and this has 2 patterns in it. And we could build a distribution like that. But of course, as we all know, just in my sort of silly example with 7 data points, there's already 2,000 combinations. If I'm looking at a genetic sequence, the sequence I'm looking at in a moment is about 20,000 basis pairs long. There's way too many combinations to enumerate. So somehow we've got to build a model that's going to actually capture all these calculations, basically sum all these different probabilities up without having to enumerate all the different combinations. Now, if you think about sampling, when we do sampling, effectively what we're trying to do is sample these with the ones with high probability and hope that we quickly converge to something that the low probability ones for our patterns are going to be not found, so therefore we will get good approximations. But for patterns, it's much harder because particular sequences with probable patterns in may not necessarily be particularly probable in their own right. So what we really want to do is somehow design it so that we can get this exactly. So what I really wanted to talk about in sort of a real application is CGP island analysis. Now, it's kind of a sort of, it's not a real application, but it's not a completely toy application either. Basically, CGP islands are segments of DNA. They occur sort of upstream from a gene, so they're nice ways to find genes in human DNA. Basically, what happens is there's some sort of frequency of CG pairs, but when a gene's present, this a methylation process, which kind of reduces the frequency, gets suppressed, so the frequency changes. So we have regions where there's a high frequency of these things and regions where they're a low frequency. We want to kind of detect them. So the most important thing about this in terms of what I'm talking about today is that CGP islands are known to be at least 100 basis pairs long, and they're separated segments. Now, if you just do some kind of classification and you go through and you just classify this, what can happen, and the classification is based on a sort of HMM analysis. You get some training data, get some estimates, define the HMM, and do the Viterbi algorithm and treat it as true, which I'll come back to in a little while when we come to the real data. We get this kind of picture. So this is my sequence along the bottom here, 18,000 pairs. It's from human DNA, chromosome 20. And what we see is we get our, the pink things are indications of where there may be CGP islands in the data. Now, all very well, we've got a nice sequence, we've got a nice segmentation. Yeah, that's great. But we've got a problem. In our definition, we said that they have to be short separated regions of at least 100 basis pairs long. Well, unfortunately, this region here is not particularly separated. So is it really one CGP island or is it two? Well, most of us looking at that would say, well, it's really one. Obviously, there's, that's an error in the middle, that it shouldn't have classified that as not CGP island, it should really be one. But how do we know that? Here, we've got this CGP island here. Unfortunately, it's 95 basis pairs long. Well, it's 95 basis pairs long in our most probable sequence. That doesn't mean that a sequence that's very, very small and slightly less probable has this at over 100 basis pairs. So therefore, it really is an island. Now, classical methods are to go, well, maybe let's just sort of pretend this is either 100, so we'll add a few to either side. Or, and in this case, well, let's just fill in the gap. But if we do that, we completely sort of obliterate the fact that this is a map estimate. There's no guarantee now that this estimate is any good at all. It could be that, in actual fact, there's a very high probability that there should be a gap here, and it might be much better to actually delete the whole thing one side or the other than to fill it in. So in some ways, we really want to sort of be able to capture the true probabilities rather than sort of taking these and kind of reconstructing them in different ways. So what we want to do is trying to sort of take this sequence and see what we can actually say probabilistically about the locations of these things. So how are we going to do this? Well, what I'm going to do is define change points. Now, for my definition of change points, it's purely going to be where the state changes. So it's the location of state changes. And I'm going to try and define an algorithm that basically finds the distribution of these state changes. The nice thing about the way we're going to define it in terms of runs is that it very, very easily allows itself to be generalized to state changes that have to be sustained for a particular amount of time, state changes that have to be in specific states, and also it allows us very easily to calculate the point at which these states change out again, so that you have both the distribution of where you change into a state and the distribution of where you come out of a state. So this would be the distribution of a start of a segment and the distribution of an end of a segment. And what you have to remember is that in some applications, that won't necessarily be the same thing, because you might start with one segment, then you may bounce around for a little while in something that you're not prepared to classify as anything before you actually enter into the next kind of block segment that you're interested in, especially if you're interested in something that needs to be sustained for a long period of time. So basically, what we can see is this is a sort of, pretend this is an underlying state sequence that happens to be here. We can see that there's very much a distinction between changes in state and runs in the data. So if we just want sort of standard change points, standard places that change where the state changes, if we look for runs of any length, so the only thing we care about is that there is a run of at least one. We can see that you can see that there are 14 runs in this data set. Some are long, this one being length 5, some are very short, just of length 1. But you also see that straight away it corresponds to the changes in state, because for a run to happen, you have to start and stop with a change in state. So we see that 14 runs correspond to 14 change points. But equivalently, if you decide that your runs must have length at least 2, you can easily determine where the corresponding sustained change points for k greater than 1 occur, because they literally correspond to the runs that occur in the data. So therefore, if we can find something out about these runs in the data, if we can actually find the distribution of where these runs occur in the data, we can actually work out where our change points are, and that then gives us our distributions for where our segments are. And the way we're going to do that is by embedding this into just a bigger Markov system. So basically, if we have the state space of the underlying Markov chain, or our hidden Markov model, we can define some kind of counter that just keeps track of what's going on. It's very simple. There's nothing tricky to do this. If you've got an rth order Markov chain because of our rth order dependence on the data, then basically we just add an extra state that kind of counts where things go along. What we're interested in doing is looking for what they call the waiting time distribution, the time it takes until something occurs. And what we're interested in knowing is that if we're looking for a run of length k, which basically just means that there is some sequence, some time t, such that before that time, at least k of these things have occurred in a row, then what we're interested in doing is trying to use this kind of embedding structure to work out this waiting time distribution. If we have the waiting time distribution, we have everything else we need. So before I actually formally define what all this is going to be about, let's have an example of how you might construct this embedding. And in actual fact, you'll see it's very simple. So say we want to search for runs of length at least 4. We're going to have a second order Markov process, and basically that means we just have a Markov chain with 2 states in it. We're going to define a new Markov chain, embedded Markov chain, and the fact by construction it's going to be Markov. It has 2 states plus the count of how far along we're going. So we initialize it with some initial distribution that's probably related to the initial distribution of our hidden Markov model. We then start counting. Well, at time point 1 we see an A, and we've seen one of them. And remember, we're looking for runs of length at least 4. So we keep going. We see 2 A's and then 2. Our state here only depends on our last 2 time points, so therefore we only need to keep these 2 A's, but we also need to keep the fact that we've seen 3 of them. But of course now we see a B, so we reset ourselves and start at 1 again. And we just keep going. And we just keep running this process, this new Markov process, until here we see 4 of the points in a row. So we say now we've seen our sustained run of length 4. So instead of now continuing to run this Markov process, we set it into an absorbing state. And it just sits in this absorbing state forever now. So it basically just sits there, and this, if we now look at the probabilities of what's happening in this process, because it's now in an absorbing state, and if this was actually hidden, so it was all probabilistic, the probability that we were in the absorbing state at any time along here would tell us about the probability that we've found one of these things. But of course we're not just interested in one of these things. So this is now sitting in an absorbing state and we can't do anything with it. What we really want to do is start a new process as soon as we hit an absorbing state. So we start this new process, but the new process has to be a little bit different to the old process. And the only reason is that we're only interested in this when it actually leaves the current run. We don't want it to sort of say, oh, well, run of length 4, well, let's find another one. And if we happen to see 4 more, say, oh, we found another one. What we want to do is we want it to wait until it comes out of the current process before starting again. So basically, we set this new chain up with in this kind of initialization state that says, I'm still going, I'm still in this run, and it's, it stays there in this new process. You see the first process is still sitting in the absorbing state and is not going to leave, but the second process is in this continuation state until it finds something that's no longer part of the run. And when it finds this no longer part of the run, it behaves exactly like the previous process did. It transitions with the same probabilities, and basically off it goes again, looking for more, and so on, and at this point it would find the second one, and at this point you would then start a new process, and you just keep defining new processes. But because of the fact this is probabilistic, basically we define new processes at every point. So you have all these different new processes going on, but because there's this nice symmetry in the fact that process 1 and process 2, after leaving the state here, behave identically, you can actually calculate them all together all at once. So you don't have to actually worry about keeping track of all these individual processes. You can actually just keep track of the sum of them together. So basically, formally, this means that we have to define some kind of state space that contains all the different possible combinations we could see of our states with the different runs of particular length, and one final absorbing state. And this final absorbing state here basically just keeps track of the fact that we've seen a run of this length. And if you're interested in particular state S, then this will be the state space. If you don't care about which state, you just want runs of a complete length, then you use this state here. So you use this state space here, which is basically just an amalgam of all the different state spaces for each individual state. Now, what you can then see is that, in actual fact, the transition probabilities for this new Markov process are completely and totally related to the transition probabilities of the true Markov process in the hidden Markov model. Basically, the transition probabilities from any state to any state in our new Z process basically depend purely on the transition probabilities of our underlying S process, the switching process in our Markov chain, conditional on the data. So of course that means that at each time point this is going to be inhomogeneous, but it will only allow to go for certain values. So for example, if you've seen 3 occurrences of something already, then you can either see a fourth one of them or you can see the first one of another one. So basically there are only certain values of J here that allow transitions, but they're exactly the same number of transitions occur in our new process than occur in our underlying hidden process for our actual model. So in actual fact, it doesn't actually grow in terms of the number of transitions, the same number of transitions occur, it's just the number of states that are possible change. And then, because this is all nice and Markov, you can see it's obviously Markov because these things purely dependent on each other by construction. The standard Markov chain theory applies. So in order to calculate our waiting time distribution, we just look to see whether our new process is in an absorbing state, and if it's in an absorbing state, then that tells us the probability of our waiting time at that time. And our absorbing states is just a particular state in our state vector. So it's very simple to calculate, very easy to look at. And we do this the same way for the next set of chains we define. We have to modify this a little bit in order to calculate the fact that we have this new continuant state, but it works very similarly. So overall, the algorithm for doing this is basically for hidden Markov models where it's independent hidden Markov switching models, other kinds of graphical model where we have it purely dependent on the states and the previous data. We form some form of inhomogeneous orthogonal Markov chain conditional on the data and the states. We embed this into a higher order system with a bigger state space, and then we define the change point distribution or the waiting time distribution or the signal segments purely by the output of this new Markov system. Now, if you've been noticing, you'll see that in actual fact I've conditioned all this on the fact that I knew the parameters of our underlying system. Now, I don't really want to talk about this because it gets kind of messy, but just in sort of one slide, estimation effects can actually be taken care of fairly straightforwardly as well. If you want to do it from a Bayesian framework, if you define a prior on your parameters, you now see that I've managed to define the change point distribution or the signal segment distribution without having to actually label up all the states. So instead of having to do the sort of standard MCMC tricks of basically including all the hidden states as extra data and then inferring them, we can actually do this directly without having to do that because we actually have the change point distribution itself. The other thing is that in actual fact, if you were wanting to optimize your model to find particular patterns, you could do this by actually looking at the marginals themselves and looking to see how your data and your marginals relate. So you can actually define parameter optimization in terms of the waiting time distributions. So let's go back to our analysis of CGP islands. As I said, so at the beginning I sort of brushed over the fact that what normally happens is that we use MLE estimates from training data and then use a HMM defined on these for new test data to identify the islands. Standard things are the Viterbi algorithm. But what we've said is that the state tree sequence is most probable. It's not the true one, so I can't just use this as if it was true because I won't necessarily get the most probable patterns. And the other thing is that this incorporation of biological knowledge, the fact that these things have to last at least 100 basis pairs long, or there has to be some kind of gap, is very difficult if you just have a single map output. So the model setup that we're going to use here is that we have ACGT, our underlying, our biological nucleotides, and we're going to label them with a plus or a minus depending on whether they're inside a CGP island or not. And In this case, it's a very simple, straightforward hidden Markov model. In actual fact, there's no error. These states completely define the output states, so A plus and A minus both give an A out. So you can see the output is just a pure classification problem. You want to infer these underlying labels. We need to use 8 states because the transitions are not homogeneous between the different labels, but it's very simple just to view this as a labeling problem of putting a plus and a minus on each of these output data. So the state space for our new chain is purely going to consist of states that are labeled with the number of pluses that have occurred of a particular length. So say that we look length k, so k in this case will be 100. We need to see at least 100 of these basis pairs in order to classify it to be a CGP island. So k here will be 100. We define a new state space which is much bigger, which has these states that look to see whether we're getting towards 100, our absorbing states, and then our states which basically reset our chain, that we're no longer in a CGP island. And what we're going to be saying is that the desired run, so the desired length, the desired segment occurs by time t if and only if our underlying Z chain is in the absorbing state. So remember, this was our most probable sequence for CGP islands. Now, depending on how you want to count, you could either have that there are 4 CGP islands here, there might be 1, 2, depending on which way you want to count it. What we can see here is the distributions of what's going on. The distribution here is the probability distribution for the maximal length island. So this is the biggest possible length island in the data, and this is the probability distribution for the number of islands in the data, conditioned on the fact that there's at least 100 basis pairs in any island. So to start with, we see here that on average there's probably a maximal length CGP island of about 200 in the data. And if we go back to our Viterbi algorithm, that seems highly likely. There's big islands here. However, the island chosen by the Viterbi algorithm here is about 360. And if we go back to our maximal length distribution, we see that that's actually very far in the tail of the distribution. It actually corresponds to this kind of bump here. So while the Viterbi algorithm gives you the most probable state sequence, it certainly doesn't give you the most probable island length. The island length is much longer in this case because the state sequence happens to be more probable with an island of that length. So it very much sort of shows that you have to be very careful about using the whole state sequence when talking about individual patterns. If you look here, so if we build the model and said, well, let's forget about the data, let's just build it unconditional on the data, what's the kind of number of islands we'd expect to see in a data set of length 18,000, we'd see that you'd expect to see maybe 2 or 3. But what we see is when we condition on the data of it being at least 100, we see that in actual fact, it seems to be that there are 3 islands in the data. And what we kind of believe that to be is there's this one, 1, 2, and 3, because we haven't taken into account that we don't really want these to be separated, that we do want them to be separated. If we actually look at the variability, these are the marginal distributions, the top 4 are the marginal distributions for the locations of the first 4 CGP islands. So what we see is that there's something happening here, there's definitely kind of distribution of the first one starting here, and the second one quite likely starts here too, and then towards the end we see maybe another 1 or 2 here. So we see the probabilities that there are 1, 2, 3, or 4 different CGP islands, and this here is literally just a sum of all these plots. In actual fact, it goes up to 20, and we see that this is basically just a probability at each location of whether a CGP island starts, so it's very likely that a CGP island starts somewhere around here, but it ends almost certainly here. The red graphs give the position of the end of the island, the blue ones give the position of the start. So the start's much more variable, but the end is much more certain. And similarly at this end. But what I've been trying to say is that in actual fact we need to take into account separation too. Well, separation is just another pattern. Separation is a pattern of seeing a length at least 100 not in a CGP island before we're allowed to start our next CGP island. So it's just another type of pattern. So I can easily incorporate it in the same framework by having 2 patterns, one of length 100 in at least 100 length for my CGP island, and then another one of at least 100 length of not a CGP island before I'm allowed to see my next CGP island. So what we see here is that with a probability of around 0.7, there is one CGP island here, but the fact that there were two quite likely, the second one was quite likely to have occurred here, when we add that restriction, it disappears. So in actual fact, there's a very low probability that there really being two with 100 separation gap here. It's much more probable there's only one. And when we get to here, we see there's, again, the high probability of there being two islands by this point, some probability of there being a third one as well. So what does that mean in terms of the number of islands in this data set? When we include the fact there should be 100 of them, include the fact that there should be at least 100 separation gap, the sort of slightly lighter grey says let's not worry about the segregation gap. The darker grey says there has to be at least 100 segregation gap. And what we see is that there's really two islands in this data set. That there's the highest probability, there might be three, but the highest probability is that there are two islands in this data set when you have to have at least 100 and have at least 100 separation gap. So we see that that's actually quite different from the argument we had from our Viterbi algorithm, because we had to know, well, do we extend it, do we put it down? Here we actually have probabilistic, true probabilistic quantification. So in summary, we've given a pattern detection methodology that incorporates error estimates. You can have a fairly general Markov dependent process. It can deal with these sort of sustained change points. In actual fact, I haven't shown it here, but it's in the paper, and you can do the joint distribution of all these different things. It basically allows you to calculate marginals, joints, all these things totally exactly. They're not based on sampling. They're not analytic, because it's an algorithmic solution, but it is an exact solution. The other thing is it's very computationally efficient. In the paper, there's actually the complexity, but basically it shows that it can be it's a very, very small number of sample equivalents in order to calculate this. For finding pure change points, it's equal to sort of 3 times the number of change points you expect in your data. For finding the sustained things, it becomes longer because the state space becomes bigger, but it's still a very small number of samples in comparison to doing MCMC sampling, where for long, long time courses with different types of patterning, you'd have to do many samples. Of course, the problem is that you only search for the pattern that you're looking for, so therefore that's where doing MCMC samples, where you can keep the whole state sequence. If you're looking for multiple patterns, it may be faster to do it that way, but certainly for searching for particular patterns, it's much more computationally efficient to look at it this way. Basically, I've showed you an example of signal segmentation. It can be used for many types of pattern detection, but signal segmentation is a very nice example. You find the location distributions, you find the distribution for the number of segments, and most importantly, you can incorporate sort of restrictions very easily into the framework so that you can actually cope with these truly and probabilistically, rather than having to sort of fudge the answer at the end once you've done the segmentation. So here are a few references, and thank you very much.
So I didn't understand this very well, but are you not changing the original model? You're constraining the HMM in some sense?
No, well, you're allowing that. So if you fix the parameters of your HMM, so you've got the standard online, then no, you're not constraining the model. You're just saying, how is that model, what does the probability distribution of the output from that model, how does it affected by restrictions that I know about? So it's not changing the model, it's just changing how do I view the output. So the HMM can give you lots and lots of different types of output. You know, the state sequence.
Surely it's constrained.
It's constraining the priorities.
It's changing the model, surely.
No, it's the model is identical.
But the probability of the sequences has changed because you're constraining the state transition.
No, I'm just ignoring any of the probability of the state sequences that don't fulfill the criteria. So I mean, it depends what you look at the model.
That's a change.
Well, I mean, it depends what you mean. It's not changing the model.
Well, that's what I would say. You're constraining your original HMM only to be allowed to make transition between particular kinds of patterns that you're doing.
No. The HMM can transition between anything it likes, but the distribution is only then counted. So if, for example, the HMM never transitions into the pattern, all I would just say is that there's no probability of that pattern being detected by this HMM. But that doesn't mean the HMM itself cannot enter a state that is not acceptable by that pattern.
Yeah, but still, whatever it is, you're still constraining I would say you're changing your original model. And the reason I say that is because there's an alternative way of looking at this,
Right.
because actually the posterior distribution of the HMM states is anyway a Markov chain, right?
Yeah.
What you could do is you could say, look, I'll take the original HMM, I just look at the posterior distribution, which itself is a Markov chain.
Yep.
And then I'll fit a hidden Markov model to model a posterior Markov chain. What that would do, it would not change the posterior distribution of the original HMM, which is what you were doing.
Well, except, so I may be misunderstanding what you're meaning, but if you've got your original HMM and you take posterior distributions so that you generate every possible state sequence that HMM can, and now I'm interested in the patterns that are generated by that. How would you now do that without changing because all I'm doing is enumerating all the ones that fulfill my criteria and adding them up, which is I don't see how that changes the model. So it's exactly the same. In actual fact, if you do Monte Carlo sampling on the original HMM, don't worry about patterns at all. Take all those samples, only look at the samples that fulfill the patterns to say, is this pattern in my data? And sum them up, you'll converge to exactly the distributions that I gave. So in that way, the model doesn't change, because if I took the true HMM and then just literally kept sampling it, it would give you the exact distribution that I'm calculating. It's purely a trick. There's nothing sort of fundamental in how the model is. It's purely a trick to work out how to keep counting things. So it's my PhD student, he likes to call it an accounting method, because it basically just takes all these lots and lots of things that I'm supposed to add up and adds them up in a very efficient way. It doesn't actually change anything, it just adds up things that you could get out by sampling, for example.
So, but do you need to rerun your original HMM?
No.
No.
No. So once you've run your HMM and you can get out your posterior transitions, then that's it. Don't ever need to look at the HMM again. So it is purely conditioned on the original underlying HMM rather than, so it's, the best way to think of it is that sample the HMM exhaustively, so you have every possible state sequence with every possible probability. Look to see which state sequences contain the pattern, and then add up the probability to those.
I think maybe you're right. I think maybe the way I would prefer to think about it is that the posterior distribution of the HMM is itself a Markov chain.
Yeah.
Which you can get from any technique will give you that.
Yeah.
And then you just analyze that posterior Markov chain.
Sure. Although in some ways you'd end up with exactly the same distribution.
Yeah, but I find it easy to think about it.
Okay, then that's definitely a way to think about it.
Okay. So I guess that you showed that for the case of runs, then you wouldn't expand the state space too much. Can you comment on sort of patterns that would be nasty for your algorithm?
Sure. So patterns where you allow lots of different combinations of things to happen. So for example, if you've got a promoter region where you believe there's a block of something happening, there may be a block of a whole lot of stuff that you don't really care about, and then a block of something else that's important. And that block of something else in the middle can have many different values. Then if you enumerate all the patterns, which is one way to do this, you can actually combine lots of different patterns together. So you can have this huge list of patterns that you search for at once. Then that would be very slow, because you'd have to enumerate all these different possibilities. But in actual fact, it's kind of equivalent to putting the separation gap in the sense that you can define lots of different new chains. So if you define a chain that searches for one pattern, then a chain that searches for something else that's not the pattern, and then another chain that searches for something else that is the next part of the pattern, by kind of adding them together in the right way, you can get around a lot of these problems. But things get complicated when you have very, very complex patterns that have many different possibilities. That will be where it would start to get very slow. But in most applications, the patterns people think about are kind of straightforward, because they believe this is going to happen or this is going to happen, and therefore, it's not particularly difficult.
No more questions? Then we have let's thank our speaker again.